This next topic we're going to discuss has to do with solving systems of linear differential equations. There are multiple ways to go about this. We're just going to talk about one, which is elimination. So, solution to a system. Okay, if we're trying to talk about solutions to a system of differential equations. A solution to a system of differential equations is a set of differentiable functions, say x equals f of t, y equals g of t, and z equals h of t, and so on, that satisfy each equation of the system on some interval. Okay, so you want to find a function, a set of functions that satisfy each equation. So what solutions do the equations share? One way to do this is by systematic elimination. Okay, it's a lot like elimination by addition that you would have seen back in algebra for solving a system of linear equations. But now we're doing it with linear differential equations. So we could look at, say, a standard linear differential equation that's, say, non-homogeneous. And remember, it has to have a couple of criteria. One is that the y prime, and so on, all those derivatives are to the first power, and then the coefficients out in front, okay, are all functions of the independent variable. In this case, let's say t. All right? We could put that in operator notation, where we replace the derivative with d. So d to the n is really the nth derivative. This is the nth minus 1 derivative. This is the derivative, first derivative, and they're all functions of y. So we could write it in operator notation. Remember, things about the operator notation that we have is that it's a linear operator, so it applies to the sum and difference rule and the constant multiple rule. So here's an example. This is a system of differential equations. There are two linear equations in both x and y, and that's really the difference here. If you think about the differential equations we've been dealing with so far, we've only had y prime, y double prime, etc., and then we had the independent variable. These now have two derivatives, x and y, both prime and double prime, etc. And then the independent variable now is t. So if you look at these two equations, this one, x double prime plus 2x prime plus y double prime equals x plus 3y plus sine t. And then you have this one as well. This is your system of differential equations. And what we would be looking for in this system is the two functions, x and y, that satisfy both of these equations simultaneously. And x would be some function of t, and y would be some function of t that we'd have to solve for. So we can take these differential equations. One thing we would do is we can dump everything in terms of x and y on one side of the equation and just have the function of t that is left over on the right-hand side. You see we did that with both of these equations. Okay. Then we can switch them into operator notation. So all the x's, if you look at the x's, switch to operator notation, and then the y's switch to operator notation. Okay? And then the same thing here with this equation and this equation. Now, if you look at it, what do we have? We have some function, some operator times x, or so let's say 4x, and some operator for y. And they have the same thing here. Well, if you look at this, this doesn't look too different than, let's say I gave you this back in algebra. 3x plus 5y equals, I don't know, whatever, 8. And negative 7x plus 8y equals 10. Okay? You have something x plus something y equals some value, and something x plus something y equals some value. We kind of have that set up here if you look at it. And you're trying to find the x and y, essentially, that satisfy this. And that's why we're going to use this notation to solve this by elimination. So we're trying to relate it to what we've seen back in algebra. So let's see how we're going to handle this. First, let's look at this example. I'll give you a really easy one to start with. dx dt equals 3y. And dy dt equals 2x. This is our set of differential equations, our system of differential equations we're going to solve. This first equation can be written as dx minus 3y equals 0. dx dt is the derivative of x. Okay, that's the dx. And then I move the 3y over, so subtract 3y equals 0. So there's that one. And dy dt equals 2x. We can write this as 2x minus dy equals 0 for the same reason. So here's our system. Okay, so we can eliminate y by operating the first equation by d and multiplying the second equation by -3. So one thing you learn with system of equations is that you could multiply each equation by some value to try and get one of the variables to cancel itself out by adding the two equations together. Well, we're going to basically do that, but we can also operate each equation by something, as well as multiplying by some constant to change the equation to remove one of the variables. So looking at this, I have dx minus 3y equals 0, and I have 2x minus dy equals 0. So if I operated the first equation with a derivative, so I apply that to this entire equation, and I multiplied the second equation by -3, okay? What would I have? Well, this distributed in here would be the second derivative of x minus 3 times the derivative of y equals the derivative of 0 would still just be 0. And then here, -3 operated on here, so multiplied times these values would give me -6x plus 3 dy equals the -3 times 0 would give me 0. So here's the now system of equations that I have, but look at what happens. These, if we added them together, would cancel each other out. So what would we have? We have this, which is the second derivative of x minus 6 times x equals, in this case, 0. And so then we could solve this. What is this? This is a single linear differential equation in terms of x. And not only that, what is it? It's a constant coefficient differential equation. So I could then solve this using the methods that we've talked about before. Then what I can do, so what I'm going to do is solve the resulting equation and get x of t as my solution. Then what I can do is I can go back to the original system, okay, and instead of eliminating y, eliminate x, okay, and then I'll find y of t. Once we have that, the only thing left to do is to find what our constants would have to be in order to satisfy the system. So we'll talk about that after we get through these first couple steps. So let's figure out what x is. Let's go back to this and we'll solve for y, and then we'll talk about these constants. So first we have the second derivative of x minus 6x equals 0. So if we did that with an auxiliary equation, okay, what would that be? Since it's a constant coefficient equation, that would be m squared minus 6 equals 0. There's no first derivative, so there's no m to the first. So we solve this auxiliary equation because it is homogeneous, right? We solve this auxiliary equation, which would be m equals plus and minus the square root of 6. Since it's a constant coefficient equation, we would get that x equals, remember x is our dependent variable, x equals c1 e to the square root of 6t plus c2 e to the minus square root of 6t. Okay, so there's the x function that satisfies this set of differential equations. Now let's go back to our system. So we have, there we go. We have dx minus 3y equals 0, and we have 2x minus dy equals 0. And think about what would we have to do to now get the x's to cancel out. Well, if I multiply this first one by -2, and I operate this one with a derivative, then I'd have minus 2 dx and a plus 2 dx, and they'll cancel out. So if I do that, I'll have to multiply this in here, here, and here, and operate this derivative here, here, and here. And what I would get would be minus 2 dx plus 6y equals 0, and 2dx minus d squared y equals 0. So through elimination, I would get negative d squared y plus 6y equals 0. So if I had my auxiliary equation for that, solving it for y, it would be minus m squared plus 6 equals 0. Okay, which actually ends up giving me the same solution, that m equals plus or minus square root of 6. And so I would have that y, because now y is my dependent variable, equals some constants. So I already use C1 and C2, I'd have to use C3, e to the square root of 6t, plus C4, e to the negative square root of 6t. And the fact that these are so similar, kind of a coincidence, somewhat because I gave you an easy example. We'll see other examples to see how this develops. But there's our two functions, x and y. Now, we have three parameters here, C1, 2, 3, and 4. What we would like to do is see if we can reduce those parameters down to, instead of 4 parameters, maybe 3 or 2 or even 1 parameter possibly. And so that's the last step. Sometimes we can't, but in this case we would like to try and do that. So that we have one more step to do, and that's to try and remove some of these parameters from this problem. But we do have our two solutions, right? These are the two functions, x in terms of t, y in terms of t, that solve this system. They're basically solutions to both equations at the same time. All right, so let's find these C1, C2, C3, C4, see if we can do anything with that. So let's think about how are we going to do that? Well, essentially the way we're going to do it is we're going to say, since these are both solutions to either one of these equations in the system, well, let's plug them in to one of those two equations and see if we can use that to eliminate some of these parameters. So which equation from the system we plug it into? Well, it depends. In this case, you try and figure out, well, which one of these two equations is simpler to work with. I don't know that either one of them is any easier than the other, so just because I feel like it, I'm going to pick the first equation, and I'm going to plug these into the first equation. And then we're going to work from there. So the first equation from our system that we chose to work with was this dx minus 3y equals 0. And so we have that x equals c1 e to the square root of 6t plus c2 e to the negative square root of 6t. And we also have that y equals c3 e to the square root of 6t plus c4 e to the negative square root of 6t. All right, so if we're going to plug these in, we have to multiply y by minus 3, okay, and take the derivative of x. So let's take the derivative of x here, okay, and then we'll plug it in to this piece, and then we'll multiply y by negative 3. Okay. All right, so the derivative, if we look at it, is going to be square root of 6 c1 e to the square root of 6t minus square root of 6 c2 e to the minus square root of 6t, square root of 6t. Okay? And negative 3 times y would be negative 3 c3 e to the square root of 6t minus 3 c4 e to the negative square root of 6t. So we plug each of these in appropriately, and it has to be equal to 0. So the square root of 6 c1 e to the square root of 6t minus square root of 6 c2 e to the negative square root of 6t plus this negative 3 c3 e to the square root of 6t minus 3 c4 e to the negative square root of 6t equals 0. Okay. So these have to equal 0, right? So if we combine these two together and combine these two together, what do we know? We know that the square root of 6c1 minus 3c3 e to the square root of 6t plus negative square root of 6c2 minus 3c4 e to the negative square root of 6t has to equal 0. Well, in order for this to equal 0, this would have to equal 0, and this would have to equal 0, so that this whole piece here would disappear, because this will never equal 0, and the same thing goes here. This will never equal 0. So, if that's the case, if the square root of 6c1 minus 3c3 has to equal 0, then basically what we could say is that c3 equals square root of 6 over 3 c1. And same thing over here, if negative square root of 6 c2 minus 3 c4 has to equal 0, then c4 would have to equal negative square root of 6 c2 over 3. Well, what we just were able to do is we were able to write c3 in terms of c1 and c4 in terms of c2, so then we could reduce the number of parameters we have. So we're going to use that, and then we can write our final answer from there. Okay, so the final answer to this system is that x equals c1 e to the square root of 6t plus c2 e to the negative square root of 6t. Okay. And y equals, instead of c3, y is going to equal the square root of 6 over 3 c1 e to the square root of 6t minus the square root of 6 over 3 c2 e to the negative square root of 6t. So there is your solution to the system. Again, replacing c3 and c4 with something in terms of c1 and c2. So we were able to reduce the parameters down as far as possible. And we can't really do much better than that. So you see, not too different than elimination by addition with your algebraic equations. Obviously, it's going to get a little bit harder than that. I gave you easy ones to start with, but that's the general gist of solving a linear system using elimination. Now, does this always work? No. It works for the easier ones. It works very well for the constant coefficient equations. But, you know, obviously there's going to have to be multiple ways of solving systems, and we were not going to get into them. We're just touching the surface here by looking at this one method. Okay, so here's another system. I already put it in operator notation for you. It should be easy to do if I didn't do that already. So, but here's another one I put in operator notation. So we're going to do the same thing we did with the last one, is we're going to try and eliminate each variable one at a time by operating or multiplying each equation by something to get the variable to cancel out. So let's look at this. If I take this, and let's say we want to get rid of the x's first. Okay? If I operate a d minus 3 on the first equation, so that's dx plus d plus 2y equals 0, and I operate a minus d on the second equation, so that's d minus 3x minus 2y equals 0, what will happen is I'll have a d minus 3 dx, and I have a d minus 3 dx, but this one will have a minus, and they'll cancel each other out. So what do we get? Well, this has to operate on the entire equation. Same thing here. So what I'll have is d minus 3 dx plus d minus 3 times d plus 2y equals 0. And then I'll have a d minus 3 dx, but with a minus in front of it. Okay, so that way they cancel out, and then I'll have a plus 2 dy equals derivative of 0 is still 0, and make sure this is a plus because a minus and a minus, And so since the x's now are gone, this is what I'll have on the left and right side of the equation. So I'll have d minus 3, d plus 2, y, plus 2d, y equals 0. So in order to solve this for y, I would have to distribute this out, collect any like terms, and then see what equation I have. So I would have d squared minus d minus 6 y plus 2 dy equals 0. So I combine this minus dy and this 2 dy, and I would have d squared plus dy minus 6y equals 0. So this is a y there as well. And so this is the equation now I have to solve. Notice that this is a second order linear differential equation with constant coefficients. So in order to solve that, if I use my auxiliary equation for this, which would be m squared plus m minus 6 equals 0, I could solve that by factoring, in which case I would have m plus 3, m minus 2. That would give me the plus m and the minus 6. So I get m equals negative 3 and m equals 2. Two distinct real solutions for this linear constant coefficient equation. Therefore, y, because that's what we're solving for here, right? Y would equal c1 e to the negative 3t plus c2 e to the 2t. So there's your y solution. All right. Now we have to go back and eliminate the y's and solve for the x's. So remember, our differential equation is dx plus d plus 2y equals 0, and d minus 3x minus 2y equals 0. So if I look at this system, multiply the first one by 2, and operate a d plus 2 on the second, that'll get the y's to cancel each other out. So what do I do? 2 distributed in here would give me 2 dx plus 2 times d plus 2 y equals 2 times 0 is still 0. And d plus 2 operated here, here, and here would give me a d plus 2 times a d minus 3x minus 2 times d plus 2y equals d plus 2 operated on 0 would still leave it at 0. And what you see is now these cancel each other out. So we're left with these x terms and 0. So we would have d plus 2 times d minus 3x plus 2 dx equals 0. Again, distribute this out, collect like terms. We get d squared minus d minus 6x plus 2dx equals 0. So combine these like terms. We get d squared x plus dx minus 6x equals 0. Again, now this is a linear equation. In x, second order, constant coefficients. The auxiliary equation would be m squared plus m minus 6 equals 0. Notice it's the same one we just had a second ago. So you're going to get m equals negative 3 and m equals 2. So our solution for x would be c3 e to the negative 3t plus c4 e to the 2t. We have to use C3 and C4 because we already used C1 and C2. So there's your solution for x. So now we have two solutions, one for x, one for y. However, we have 4 parameters that we would like to reduce as much as we can. How? We're going to take those two solutions, one for x and the one we had for y. Y, if you remember, was basically the same as x. It's just C1 e to the negative 3t plus C2 e to the 2t. We're going to take these two solutions and we're going to plug them into one of these two equations. Okay? It doesn't matter which one, pick one and then go from that. I'm going to choose this second equation. The reason I'm going to choose the second equation is I have less derivatives to deal with. This one I'd have to take the derivative of x and the derivative plus 2 for y. Here I only have to do the derivative minus 3x and minus 2 times y. I feel like this is simpler for me to work with, so I chose that one. You could have very well chose the first equation, but we're going to plug these in and see what happens. So here I need to operate d minus 3 on this equation, which means I have to take the derivative of this equation and then subtract 3 times this equation. Okay? And here I just have to do minus 2 times this equation. So again, the equation I'm going to work with is this d minus 3x minus 2y equals 0. So x, again, if you remember, c3 e to the negative 3t plus c4 e to the 2t. So I need to do the derivative of this. Okay, that's what this is, the derivative of this. So x prime. And I have to do minus 3 times x as well. Okay? And then I'll also have to do minus 2 times y. Okay? And those are the 3 things I'm going to need. So once I have these 3 things, I could write this as x prime. I could also write this as dx if you want. It's the same thing. Then I can plug them in, and it should equal 0. So the derivative of x. So this will be negative 3c3 e to the negative 3t plus 2c4 e to the 2t. Negative 3, 2t. Negative 3 times x is just negative 3c3 e to the negative 3t minus 3c4 e to the 2t. And negative 2 times y, if you remember what y was, that would be minus 2c1 e to the negative 3t minus 2c4 e to the 2t. So these are the 3 pieces I need. That is this. It should equal 0. So this plus this should equal 0. So negative 3c3 e to the negative 3t plus 2c4 e to the 2t minus 3c3 e to the negative 3t minus 3c4 e to the 2t minus 2c1 e to the negative 3t minus 2c4 e to the 2t. That should all equal 0. Well, obviously I got to put a lot of this together, so I'll take this, this, and this. They're all using negative 3t terms. I'll put them together. So I have negative 3, negative 3c3, so that's going to be negative 6c3, and then I have a minus 2c1 e to the 3t, e to the negative 3t, and then the same thing I'll do here is this, this, and this all go together. Okay. Actually, sorry, this one, if you remember, this one should have been C2. So what are we going to have here? So these two will give me negative C4 minus 2C2 e to the 2t. That should equal 0. So just like the last one, because this has to equal 0, this has to equal 0, and this has to equal 0. So that will give me that either C1 or C3. It doesn't matter which one we solve for, honestly. It really doesn't. This would tell me that, negative 6C3 minus 2C1 has to equal 0. So if I solve for, say, C1, I would get C1 equals, what, negative 3C3. And over here, negative C4 minus 2C2 has to equal 0. So let's say we solve for C2. We would get C2 equals negative 1/2 C4. So once we have that, and again, it didn't matter if I solve for C3 or C4 or C1 or C2, just solve one in terms of the other. So then if I take these and I plug them into my solution, we would find out that y equaled C1 e to the 2t, e to the, oops, that one's negative 3t, right? E to the negative 3t plus C2 e to the 2t. But because of what we just came here, we could actually write that as negative 3C3 e to the negative 3t plus or minus 1/2 C4 e to the 2t. So that's your y, and your x was just C3 e to the negative 3t plus C4 e to the 2t. Okay. This is just 2 here. So there you go. So there's your two solutions in terms of two of the variables, in this case C3 and C4. We did in C1 and C2. Ultimately, it doesn't really matter, but those are our solutions. Okay, we have one more. Now this one's a little bit harder for the primary reason that both of these equations in the system are not homogeneous. Notice this. That's the difference between this system and the two previous systems we just looked at. So the second you get into non-homogeneous, we all know, things get a little bit longer. But this is going to use all the same stuff we've been using all semester, so we can handle it. All right, so let's look at this. First thing, put it in operator notation. So if I put this in operator notation, I'll have d minus 4x plus d squared y equals t squared, and d plus 1x plus dy equals 0. Okay, that should be no problem. Next thing I want to do is I want to eliminate one of these variables. Doesn't matter which one we do first, we're going to eliminate both of them. So let's eliminate, let's say the y's. That's a pretty easy one. If I operate this with a d, they'll have d squared and d squared. I just need to switch the sign of one of them to be a minus, and then I'm done. So I'm going to operate this second equation with a negative d. So what I'm going to have is I'm going to have d minus 4x plus d squared y equals t squared. Then I'll operate the second one with a minus d, so I'll have a minus d times d plus 1 x minus d squared y equals, this minus d operator on 0 would be 0. And so what that allows me to do is to cancel these. This side I would have this, and the other side I would have this added together. So what do I get? I get d minus 4x minus d times d plus 1x equals t squared. So I have to distribute all this out, collect like terms. So I have dx minus 4x minus d squared x minus dx equals t squared. So these cancel each other out. So I end up with minus d squared x minus 4x equals t squared. So that's now the differential equation that I need to solve. It is constant coefficient on this side, but it's non-homogeneous. So what are we going to do? We're going to first solve the homogeneous version of this. So we're going to solve minus d squared x minus 4x equals 0, and that'll give us y sub c. Then we're going to have to solve the non-homogeneous component to this by finding y sub p, and this is able to be annihilated, so we could do that, or we could do variation of parameters. So let's first get y sub c. So my auxiliary is minus m squared minus 4 equals 0. So that's going to give you m squared equals negative 4, so m equals plus and minus 2i. So being that that's an I, y sub c, sorry, x sub c in this case, right, because x is our dependent variable here. X sub c would be alpha is 0, beta is 2. So we'd have c1 cosine 2x plus c2 sine 2x. That's the first piece. Then we need y sub p, or sorry, x sub p. I'm going to choose to do the annihilator method. It's a pretty easy function to annihilate. d to the third derivative will annihilate it. So if I apply that annihilator to this equation, which would then be minus d squared x minus 4x, I would get 0. So then if you look at this equation, this is what we already had. We already know the roots to that equation, plus or minus 2i. This is the new piece. If you notice, it doesn't share any roots with the original, so we can really just say y sub p is going to be based off of that. That would be, m equals 0 repeated 3 times. So our y sub p's form, or x, I keep saying y, just have it, x sub p would be C3 e to the 0x plus C4 x e to the 0x plus C5 x squared e to the 0x. And I'm not writing e to the 0x because we know that's 1. So that's the form of x sub p in order to plug this into the differential equation and figure out what C3, 4, and 5 are, because remember that's something you have to do. What I'm going to do instead is I'm going to take the derivative of this and the second derivative and plug it in here, and then we'll go from there. So x prime sub p would be C4 plus 2C5 x, and x sub p double prime would be 2C5. Okay, so we're going to need to take this, we're going to plug it into here, okay, and we're going to figure out what these values are. So we have minus d squared x minus 4x equals t squared. So negative, and remember we have x sub p double prime equals 2c5, and x sub p itself is c3 plus c4x plus c5x squared. So we have to take negative times the second derivative. So this would be minus 2c5, then minus 4 times x itself, so that would be minus 4c3 minus 4c4x minus 4c5x squared. I'm all over the place here. These should not be x's. These should be t's, because x is a function of t. And that equals t squared. Okay. So here's your constant, here's your t to the first, here's your t to the second. Well, this has to equal 0, this has to equal 0, and this has to equal 1 because of what's over on the other side of the equation. So if minus 4c5 has to equal 1, then c5 has to equal minus 1/4. And if minus 4c4 has to equal 0, then c4 has to equal 0. And then if minus 2c5 minus 4c3 has to equal 0, but we already know c5 is minus 1/4, this would be 1/2 minus 4c3 has to equal 0. So then c3 would have to be 1/8. So that tells me that x is going to have to be c1 cosine 2t plus c2 sine 2t plus 1/8 minus 1/4 t squared. X sub c, x sub p. All right, so there's 1. Okay, now we got to do the whole thing over again for y. And then eventually, maybe we'll try and get rid of some of these parameters, C1, C2. All right, let's do this all over again for y. So let's get back to our original differential equation in operator notation. D minus 4x plus d squared y equals t squared. And d plus 1x plus dy equals 0. Okay, we're going to try and eliminate the x this time. Well, we would have to operate a d plus 1 here and a d minus 4 here, and one of them is going to have a negative in front of it. Let's just put a negative on that one. And so that has to operate through each equation. So if this operates through this equation here, here, and here, what would we get? Well, we would get d minus 4 times d plus 1 x plus d squared times d plus 1 y equals d plus 1 operated on t squared. That's the derivative of t squared, which is 2t, plus 1 times t squared, which is t squared. Okay? And then that same thing operated on the next equation. So we would have a minus d minus 4 d plus 1 x, and that was so that these can cancel. Okay? Then we're going to have a d times, or sorry, a minus, let's not lose that minus, minus d times d minus 4 y equals, this operated on 0 would still give it 0. So this is what we're left with now. So we have d squared times d plus 1y minus d times d minus 4y equals 2t plus t squared. Distribute, distribute, and let's see what we have. So we get d cubed plus y plus d squared y minus d squared y plus 4y equals 2t plus t squared. So notice these cancel. So we have d cubed y plus 4y equals 2t plus t squared. So that is the differential equation we need to solve. Notice it's a third order, non-homogeneous, but it does have constant coefficients, so that's a benefit. So what are we going to do? We're first going to find y sub c, and then we're going to find y sub p. So to find y sub c, we need the auxiliary equation, which in this case is m cubed plus 4 equals 0. Wait, I see a mistake. Where's my mistake? Well, here's my mistake. It's right here. This times this would be 4dy, which would put a d here, which makes quite a difference. We got to try and be careful to simplify as best we can without making any mistakes. Well, I caught that one before it really got out of hand, so we're good. All right, so let's see here. We're going to have m cubed plus 4m equals 0 as our auxiliary equation. So m times m plus 4 equals 0, or m squared plus 4, so m equals 0, and m equals plus or minus 2i. So we get 3 solutions. So our y sub c is going to be, well, think about it. We already used C1, C2. We did use C3, C4, C5, but then we solved for those. So, I'm going to go ahead and use those. So let's say C3 e to the 0t, so C3, plus C4 cosine 2t plus C5 sine 2t. All right, there's your y sub c. But then we need to figure out what y sub p is. How? Let's do elimination again. If we annihilate this thing with a d cubed, okay, then we can go ahead and find the form of y sub p and then solve for y sub p's components. Okay, so we have the equation d cubed y, third derivative of y, plus 4 times the derivative of y equals 2t plus t squared. So I'm going to annihilate that. I'm going to annihilate it by a d to the third derivative, operated on what's already here, annihilates the right-hand side. So then the auxiliary equation that we get from this is m cubed times m cubed plus 4m equals 0. Notice we then have an m to the 4th times m squared plus 4 equals 0. And so we're going to get m equals 0, but now that's repeated 4 times, and we have m equals plus or minus 2i. Well, think about this. M equals plus or minus 2i, and one of these m's came from y sub c. So y sub p would start with the next m, okay? So that would be the first time it's repeated. So what are we going to use? We're going to use C6 T, okay, plus C7 T squared plus C8 T cubed. So that's the second, third, and fourth time this 0 is repeated. Remember, the first time it happened was with y sub c, so there's our y sub p. Okay, well, in order to plug this back into the original differential equation, we need to get up to the third derivative. So y sub p prime, y sub p double prime, y sub p triple prime. Y sub p prime would give me c sub 6 minus 2c7t plus 2c7t plus 3c8t squared. And then the second derivative would be 2c7 plus 6c8t, and then the third derivative would be 6c8. All right. The nice thing is none of these derivatives are very difficult. So we're going to take this, plug it in here, take 4 times this derivative, and plug it in here, and it should equal 2t plus t squared. All right, so what do I have? What I have is 6c8 plus 4 times the derivative, remember, was c6 plus 2c7 t plus 3c8 t squared. That has to equal 2t plus t squared. So we have 6c8 plus 4c6, that's our constant, plus this will give me 8c7t, and then this will give me 12c8, 12c8t squared equals 2t plus t squared. All right, well, based off of what's happening here, 1 in front of t squared, 2 in front of the t, this would have to equal 1, this would have to equal 2, and this would have to be 0. There's no constant on the right-hand side. So working our way backwards here, this tells me that C8 has to equal 1/12. This tells me that C7 has to equal 2/8, which is 1/4. And here, since C8 equals 1/12, this would be 1/2 plus 4C6 has to equal 0, because it would be 6/12. And then that means that C6 would have to be minus 1/8. So that's going to get me my y sub p, which, if you remember, was going to be minus 1/8 t plus 1/4 t squared plus 1/12 t cubed. So then y, being y sub c plus y sub p, would be c3 plus c4 cosine 2t plus c5 sine 2t minus 1/8 t plus 1/4 t squared plus 1/12 t cubed. So there's your y. Okay. Now y has 3 parameters in it, c3, c4, c5, and x, if you remember what x was, okay, x had 2 parameters in it, c1 cosine 2t plus c2 sine 2t plus, what else do we have there? It was minus 1/4 t squared plus 1/8. I believe that's what we had. Those are our 2 solutions, but we have 5 parameters. Okay, can we reduce the number of parameters? Well, I think we can reduce C4 and C1 and C2 and C5 because they're both with cosine and sine. I don't think C3 is going to be able to reduce anymore. How are we going to reduce them? Well, we got to plug them into one of the original differential equations. Not the best thing to have to do, but we can do it. Okay, so if we want to reduce the number of parameters we have to plug it into one of the original differential equations. It's going to require us to take the derivative of each of these, and once we do that, then we're finished with this problem. But this was a pretty ridiculous one. I mean, if you look at what's happening, it's 2 non-homogeneous linear differential equations basically in one problem. But all things we've learned before. Okay, so to finish this off, let's see. We're going to pick one of the original differential equations. I'm going to choose this one, x prime plus x plus y prime equals 0. Why did I choose that one? There's not really a great reason. This one has smaller derivatives than the other equation did, so I felt like this would be a little less work to plug our solutions into to try and find our C1, 2, 3, 4, 5 connection. So let's look at it. We got x was one of our solutions, and that was C1 cosine 2t plus C2 sine 2t minus 1/4 t squared plus 1/8. And I'm going to need the derivative of that because of this. So let's just do that right now. X prime would be minus 2 C1 sine, sine 2t plus 2 C2 cosine 2t minus 1/2 t, and then that'll be plus 0, so that we're not going to write. So there's your x prime. And then remember, there was also y, which was C3 plus C4 cosine 2t plus C5 sine 2t minus 1/8 t plus 1/4 t squared plus 1/12 t cubed. And we're also going to need the derivative of that for this piece. So there's y prime. So what are we going to get? Well, C3 is going to go away because it's a constant. We're going to get minus 2 C4 sine 2t plus 2 C5 cosine 2t minus 1/8 plus 1/2 t plus, this will be 3/12, so what's that, 1/4 t squared. All right, so we're going to take this and plug it here, this and plug it here, and this and plug it here, and the sum of all that should equal 0, okay? So, what we're going to look at is that this plus this has to 0 out. Well, we can kind of do this and condense it all at once. So if you look at it, if we're adding them together, we're going to add the cosines together, we'll add the sines together, and so on. So here's a cosine term, here's a cosine term, and here's a cosine term. So they're going to add together. So what do we get? We're going to get C1 plus 2C2 plus 2C5 cosine 2t. And then we have our sine terms. Let's find another color. There's this one, plus this one, plus this one. And you see we're going to get C2 minus 2C1 minus 2C4 sine 2t. Okay, what do we have next? what we have next is, let's say, our constants. Well, we have 1/8 and we have minus 1/8. So they're going to cancel each other out. So that's good. Then t to the first. I have a minus 1/2 t and a plus 1/2 t. Okay, they're going to cancel each other out. So that's good. Then I have my t squared. Well, guess what? I have minus 1/4 t squared and a plus 1/4 t squared. They're going to cancel each other out. So all I'm left with is then 0 on the other side. So we added this, plus this, and this is where we are. So what's going to happen is, because it's equal to 0, this is going to have to equal 0, and this is going to have to equal 0. So we can write this here, if this whole thing equals 0, we could basically solve for C5 in terms of C1 and C2. So we could say that C5 equals negative C1 minus 2C2 over 2. And this one we can solve for C4, in which case we could say C2 minus 2C1 over 2 equals C4. And what that gives us is essentially we can get rid of C5 and we can get rid of C4, writing in terms of C1 and C2. Now each one has to be written in terms of both of them, but still we were able to eliminate 2 parameters from our final solution. So our final solution is, we're finally done here. The final solution is x equals C1 cosine 2t plus C2 sine 2t minus 1/4 t squared plus 1/8. Okay, so there's that. And then y, okay, so let me change colors. Let's say, I can go with green. Y is our other solution, and y equals C3, couldn't do anything there, but C4, which is C2 minus 2C1 over 2 times cosine 2t, plus C5, which is negative C1 minus 2C2 over 2 sine 2t. And then I'm going to have to start writing up this way, basically plus all this other stuff. So minus 1/8, yeah, this is the problem with trying to do this on this little screen. Minus 1/8 t plus 1/4 t squared plus 1/12 t cubed. Okay? Yeah, obviously if I had a nice big board in the classroom, I could do this a little bit better, but this is where we are. But anyway, that's it. There's your solutions. That was the final step here. Clearly you see that some of these problems can take quite a bit of time to solve. But as far as solving them, none of the steps were very difficult. They were all things that we have done multiple times before already in this semester. And things you used in algebra like elimination is the same concept here as well. Now there are other ways to solve systems of linear equations. What do these equations all have in common? Well, the thing that all these equations have in common is that they were all constant coefficient equations. Yeah, they had 2 variables, x and y, were basically 2 functions you had to find. They were all fairly simple equations in that they were basically constant coefficient equations. As the system gets more complicated, this elimination process doesn't work out very well. It really starts to break down. We would have to look at more complicated ways of solving a system of differential equations. And this is where, you would have to use a background in linear algebra to really kind of get into this. And so that's where linear algebra and differential equations really starts to overlap and come together. That's kind of beyond where we are right now with doing that, mainly because we're out of time in the semester, but that would be kind of the next step in the evolution of kind of working in differential equations, besides talking about partial differential equations.